Hello everyone, my name is Nihal Sunil Navale and I'm a first year master student pursuing robotics engineering at Worcester Polytechnic Institute, and this is my individual paper reading assignment for motion planning course. So the paper that I'm going to be talking about is path planning for mobile robots using bacterial potential field for avoiding static and dynamic obstacles. In this paper, the optimal path for static and dynamic obstacle avoidance for a mobile robot is computed using a new method called Bacterial Potential Field, also known as BPF. It ensures a feasible, optimal, and safe path. BPF is a combination of artificial potential field APF and the bacterial evolutionary algorithm BEA, hence the name BPF. BEA takes all the advantages of artificial potential field and strongly reduces its disadvantages. And in this paper, we'll also be having comparative experiments with the classical artificial potential field and pseudobacterial potential field PBPF and genetic potential field GPF. PBPF and GPF are parts of the evolutionary artificial potential field. Methodology. This methodology deals with motion planning that includes two different but complementary tasks, which are path planning and trajectory planning. The first one consists of designing a dynamical system that can drive the mobile robot from an initial position or state to a target position or goal, whereas the trajectory planning focuses on determining how to move the mobile robot along the solution given by the path planning algorithm in a way that the mechanical limitations of the mobile robot are respected. The path planning with BPF proposal allows the mobile robot to navigate in an autonomous form without being trapped in local minima, which is one of the disadvantages of artificial potential field, making the BPF proposal suitable to work in dynamic environments, which is also very crucial in real-world applications. Some significant advantages of the bacterial potential field over the original artificial potential field method, as well as its derivatives with the evolutionary artificial field potential field. So this is the comparison table between the various methods: artificial potential field, evolutionary artificial potential field, and bacterial potential field. On the left, we have all the tasks that we need for a planner to have, such as local planning, smooth path, global planning, automatic gain search, small time consumption, and all the various others. So here you can see that artificial potential field only gives us smooth planning as well as uh, local planning, whereas evolutionary artificial potential field has a lot more, but the best would be bacterial potential field, which does satisfy all the criteria given here. Robot motion planning can be tracked down to the middle of 1960s, where it was dominated by classical approaches such as roadmap, cell decomposition, mathematical programming, and artificial potential field. Roadmap method is made up of Voronoi and visibility graphs. In the visibility graph, which is a collection of lines in the free space that connects the trait of an object to another. In Voronoi diagram, it is a collection of geometric objects in partitions of spaces into cells, each of which consists the point closer to one particular object than the other. The idea of cell decomposition algorithm was to decompose the C space into a set of simple cells and then compute the adjacency among cells. Whereas in the mathematical programming approach, the requirement of an obstacle avoidance is represented by a set of inequalities on the configuration parameters. The idea is to minimize certain scalar quantities to find out an optimal curve between the start and the goal position. The artificial potential field concept was introduced by Khatib in the year 1986. At the beginning, this method was used for obstacle avoidance in path planning for robot manipulators, but through time, it has well been adopted for mobile robots and group of mobile robots. One such example is robot swarm formation, obstacle avoidance, and swarm movement control as a whole using artificial potential fields. In this, an MR mobile robot is treated as a point represented in the configuration space as a particle under the influence of the fields. Artificial potential field method is used as by establishing an attractive potential field force around the goal point, as well as establishing a repulsive potential field force around the obstacles. Both of these fields together make up the total potential field, which is named artificial potential field. And in the year 2007, Masayana and Sekhizadeh uh, read around 1,381 papers or reviewed 1,381 papers from the year 1973 to 2000, and they were covering a significant depth of works in the robot motion planning field. In this work, a broad classification of different techniques were presented, and this will be talked about in the next slide, where the classification was made into three main parts: probabilistic, heuristic, and meta-heuristic approaches. In this work, a broad classification of heuristic techniques is presented, which facilitates the analysis and method expectations. Broadly, the given classification is as follows: probabilistic, heuristic, and meta-heuristic. With in heuristic and meta-heuristic approaches, they have neural networks, genetic algorithms, simulated annealing, and many more. All the mentioned methods have their own strengths and drawbacks. They are deeply connected to one another, and in many applications, some of them are combined together to derive the desired robotic controller in the most effective and efficient manner. In this paper, the bacterial potential field is proposed as a method for path planning for mobile robots. It ensures a feasible, optimal, and safe path for the robot navigation. The bacterial potential field method uses concepts from artificial potential field, mathematical programming, and meta-heuristics to solve efficiently a robot path planning problem. It ensures a reachable configuration set and controllability if it exists, or performing current artificial potential field approaches. The artificial potential field is a reactive motion planning method with inherent, well-known difficulties to travel finding global optimal paths because it cannot solve all the local minimum problems. So how do we solve these problems in the artificial potential field? One thing what we can do is we can combine artificial potential field with other methods such as evolutionary algorithms, and this gives rise to what is called as evolutionary artificial potential field, EAPF. You can also combine artificial potential fields with genetic algorithms, which will give rise to things like, or algorithms like pseudobacterial genetic algorithm, PBGA. The BEA, which is bacterial evolution algorithm, which is the basis of bacterial potential field, is based upon pseudobacterial genetic algorithm. So pseudobacterial genetic algorithm is one of the foundations for BPF methods. So BPF gives us faster convergence and improvements in the solution. Path planning is generating a collision-free path, which is a feasible path in an environment with obstacles, and optimizing it with respect to some criteria such as distance, time, energy consumed, and many more. The next points are taken into consideration for development of the bacterial potential field path planning method. The first is the path P. It is a set of configurations Q named from Q0 to QF, with QF being the start position and QF being the target or goal configuration or state. Second, since having a reachable configuration set and controllability are intimately related, the former must exist in order to accomplish the control task of steering the mobile robot through the configurations queue, fulfilling the requirements of the total time T, which is sigma 1 to m, TST. TST implies that the system can go from any point in P in a time TP plus TJ. TP is the time taken to calculate the path. TJ is the time consumed by the trajectory planner. For static environments, TP is 0 since there is no changes in the scenery. However, for dynamic environments, TP rises its importance since slow path planner will not justify or satisfy the local and global controllability criteria. Now, bacterial potential field is an original path planning method that uses potential function as a cost function to find optimal paths. Bacterial potential field and artificial potential field methods have common mathematical foundation. So let's take a look into the similarities or differences. The first, that the mobile robot is in the 2D Euclidean coordinate system. Second, the mobile robot is modeled by a circle of radius r and orientation theta, but in the Bacterial Potential Field, the robot is considered to be a point, hence the radius is 0. Both the methods need a start point Q, goal point QF, and obstacles O1, O2, and so on till On. They both use potential function U total, which is addition of U attraction and U repulsion, which is shown here. And U attraction is given by the following formula: half of Ka Q minus Qf whole squared, and U repulsive is half Kr 1 over rho minus 1 over rho whole squared if rho is less than or equal to rho naught, and 0 if rho is greater than rho naught. So rho naught is the limit distance of influence of the potential field. Rho is the shortest distance to the goal, and Ka and Kr are the scalar variables that represent the attractive and repulsive gains respectively. The mobile robot navigates the total force. Mobile robot navigates the total force given by Fq, which is minus delta U total of Q. In the next few slides, we'll be talking about the various algorithms which make up the bacterial potential field method, as well as the navigation of the mobile robot which uses bacterial potential field. Okay, so now we'll talk about the algorithms. The backbone of this novel proposal is the use of bacterial evolutionary computation, which enables the mobile robot to find at a low computational time the optimal values of Ka and Kr that correspond to the attractive and repulsive forces. This characteristic is very important since it allows the mobile robot to navigate without being trapped in the local minima, making BPF method suitable to working dynamic environments. Here in algorithm 1, the pseudocode of the BPF method is given. The proportional gains evolved by means of the VEA, which uses the APF method, that is explained in algorithm 3 as the fitness function. Here you can see various variables var1 until var(n). The fit value for the optimal is equal to BEA of various variables, the BEA parameters and the fitness function, and NP. Where at the right hand of the function var1 till n are the parameters that are going to be optimized using specific mutation rate, number of infections, number of bacteria, etc., with the aim of fulfilling an optimization criteria according to the fitness function given by fitfunc. NP is the number of processes to be used. The returning values are optimized variables var1 till varn, and the corresponding fitness value, fit value. Therefore, the input parameters of the BPF method are those required by BEA and APF algorithms. In line 2 of algorithm 1, a fitness function handler, fitfunc, is used to facilitate the pseudocode writing. It is equivalent to write the APF method function, including all its parameters, which is given in algorithm 3. In line 3, the BEA evolves the parameters Ka, Kr1 until Kar, Krn, and eta to obtain the corresponding optimal values if the goal was achieved. That is, if goal is 1. In this case, the DA value, the user can verify that the mobile robot has reached the goal. That is, DA is less than or equal to epsilon. Otherwise, it returns goal equal to 0, which means the goal was not achieved. And in this case, the BEA returns the best value found so far. DA to the obstacle to know how far the mobile robot is from the goal. For the case when goal is equal to 1, lines 4 to 9 are to emphasize that the APF function in line 9 will use the optimal values to perform the desirable path planning. When goal is equal to 0 in line 10, special programming instructions can be included to indicate that the fact that the goal was not achieved. The bacterial evolution algorithm BEA introduces two operations inspired by the microbial evolution phenomena: the bacterial mutation operation, which labor is to optimize the chromosome of a single bacterium, and the gene transfer operation to provide the transfer of information between the bacteria and the population. In algorithm 2, which is intrinsically parallel, The divide and conquer strategy can be applied in many different ways. We have used a single population master slave approach in which one master node executes BEA operations working on a single population P dash of T, and the fitness value evaluation of the individual P dash of T is divided in Pi of T subpopulations distributed among several slaves in the processes. For the particular case where the input parameter NP is 1, we have the sequential implementation. The other input parameters are an array of variables, variable 1 to variable n, that will conform the bacteria. The BEA parameters are contained in BEA param, which the information about the mutation rate, number of infections, stop condition, etc. are given, and the fitness function fitfunc. The algorithm will return an array containing the optimized variables and the best fit value found. The APF method has great advantages in the path planning for robots, where the basic inputs from the users are the starting position, the goal position, and the value of attractive and repulsive potential gains. In this work, algorithm 3 is based on APF approach, and it has been designed to be used as fitness function for the proposed BPF method. The algorithm requires the next set of values: a starting position Q0, a goal position Qf, the proportional gains Ka and Krn, which are the gains of attractive and repulsive potential respectively, and represents the number of obstacles. The step size eta used in the iterative calculation of the next position Q, which is step 7. The convergence radius epsilon, that can also be given by the user as an input to the algorithm. And the maximum number of iterations m, which represents the robot configuration position. The parameters epsilon and m are the algorithm stop conditions, as it is shown in line 4. Note that depending upon the number of obstacles, several Kr1 till Krn repulsive proportional gains may exist. In the APF, the Ka and Kr gains are provided heuristically, therefore for being compatible and achieving fair comparisons against the APF. Only one Kr is used for all obstacles. The algorithm starts calculating the Euclidean distance dA to determine dE distance between the mobile robot position and the goal position. Next, it enters into a loop to move the mobile robot step by step. Inside the loop, the potential U total of Q is calculated using the equation of step 5 based upon 2 and 3, where n is the number of obstacles, and in step 6 it calculates the negative gradient U total of Q to obtain the generalized force F of Q. Step 7 to iteratively calculate the new positions of the mobile robot. Step 8 is calculated the new existing distance dA between the actual mobile robot position and the goal position. The loop iterates until the stop conditions are presented, and from step 11 to 17 the algorithm verifies whether the mobile robot reached the target or not and returns the path planned. For the failure case, the target robot has not been achieved, and probably the mobile robot was trapped in a local minimum problem, trajectory prediction problem, or on a goal non-reachable problem. These are the most common problems faced by the APF method, but successfully solved by the bacterial potential field method. So this is the navigation or implementation algorithm, and it is used by the mobile robot to navigate from the start to the goal position. The navigation algorithm uses BPF algorithm for path planning before and during the navigation. Before the navigation starts, the BPF algorithm is called to get the path that will drive the mobile robot. At this first stage, the path planning is known as offline path planning. Then, when the navigation has started in the while loop, the mobile robot is driven point to point, following the points collected in the path P. The BPF algorithm will be called when the environment suffers a change. Example, some obstacles are added or removed or moving. In this stage, the process is known as online path planning, And line 13 in the algorithm remarks that it is necessary to achieve trajectory planning for real robots before they navigate from point pi-1 to point pi. As it is mentioned before, the trajectory planning depends on the mobile robot architecture and consumes a time tj. For the case of the simulator, which is shown in the figure, tj is equal to 0. Now let's take a look into the various experiments and also analyze the results from the experiments conducted. Now for experiment 1 or test problem 1, which is to solve the local minima problem which is seen in the artificial potential field. On the left in figure A, you can see that the robot is stuck in a local minima while traveling from the start to the goal position. Whereas in figure B, you can see that this problem has been solved by 3 different methods, which is PBPF, BPF, and GPF. Hence, from all out of these 3, you can see that the bacterial potential field gives the most optimal path with gains Ka and Kr much lesser than the other 3 methods, and distance being equal to GPF and PBPF, with path length being 7.938, which is relatively lesser than the other 3 methods. And the number of configurations is 391, which is also lesser than the other 3 methods, and it does reach the goal. So that's really 1 up over the APF, and it has no collisions. So the test problem 2, which is trajectory prediction. In figure A, you can see that the robot is not able to reach the position when it goes from start to the goal. It overshoots from the goal position, and this might be because of more repulsive forces than the attractive force at the goal. So in the first figure, artificial potential field is being employed, whereas in figure B, you can see that the other methods such as PPF, GPF, and PBPF have been employed. And here you can see that the robot does reach the goal position. And out of all these 3, BPF method is the most optimal, as it has the least path length and the number of configurations is lesser than compared to the other methods. The first 3 test problems illustrate how well performs the bacterial potential field proposal, beating the inherent limitations of the classic artificial potential field method. And in the test problem 3, which is goals non-reachable with obstacle nearby, in this scenery, it is a bit different from the local minima problem in that the global minima is being pushed away from where it is supposed to be, that is the goal point, into another position. As a result, the mobile robot cannot converge to the correct point, which is the goal. This problem in literature is also known as goals non-reachable with obstacle nearby. And here we have 3 obstacles which recreates a real world wall, which is as shown here. And table shows a summary of the results for the 4 methods for GPF, PBPF, and BPF. In the APF method, it uses heuristic knowledge. We choose unlucky values such as Ka equal to 4 and Kr equal to 25. Hence, the mobile robot gets involved in the goals non-reachable problem. Hence, the algorithm 3, after trying for 2000 iterations or 2000 configurations, it declines to continue, and so it stops, and the mobile robot is non-controllable. Whereas in the GPF method, it effectively reaches the goal, and the same is seen in PBPF, and it also provides an optimal path, but it requires more configuration positions than the bacterial potential field. Moreover, it provides a shorter path than the GPF method. BPF, in this is the best method to solve this problem. It needs fewer configuration positions and it provides the shortest path. Figure C illustrates the optimal path taken by the BPF algorithm, And you can also see that it chooses the appropriated gains effectively and avoids to fall into the goals not reachable with obstacle nearby problem. It is also revealed that the BPF is quite faster in optimization, leading to a reduction in computational burden. Test problem 4: online path planning for unknown environments. An advantage of the offline mode is that environment is known. However, real-world applications frequently face the mobile robot to unknown or partially known environments, where the already planned path needs to be adjusted for reaching the goal fulfilling the controllability criteria. This operating mode is referred to as online. In this experiment, we are going to place an object or obstacle at random in such a way that it blocks the already found optimal path, interfering with the mobile robot trajectory. In this case, the random obstacle must remain static once it was put. At the beginning of the experiment, the environment is known. There are 5 obstacles placed at the shown spaces or positions, forming a 2-wall obstacle to recreate a real-world corridor. Now, first, the path planning is achieved in an offline mode because the environment is known, which is shown in figure A. And then figure B, we switch to the online mode and the navigation starts. At the beginning of the mobile robot follows the path plan in the offline mode as shown. Afterwards, an obstacle is added in between the obstacles to make a change in the environment or world configuration for the mobile robot as shown in figure B. And the mobile robot senses the obstacle, then calculates the obstacle position to update the world configuration. The path planner of the mobile robot now has different world configuration, hence it's necessary to update the path by recalculating the set of gain parameters. And now the mobile robot follows a new path to reach the goal as shown in figure C. Table shows a summary of the obtained results. In GPF, this method can find optimal paths avoiding collisions. The path length is comparatively as good with the other two, PBPF and BPF. Though it requires more configuration positions than the other methods, it is slower and can be seen in the following table. PBPF is almost the same as GPF, but it will require lesser Q positions, and it is practically as fast as bacterial potential field. Bacterial potential field method provided the best results. It needed less Q positions than the other two methods consistently throughout the experiment, but it is still being the faster, shows that the computations for the sequential and parallel implementation, and it does perform really well when in online and while avoiding obstacles. Test problem 5, which is online path planning for unknown environments with dynamic obstacles. The interaction with the real world requires the ability to respond and take decisions over the changes in the environments. In this test problem, it is a bit different to the previous test problem, where the random obstacle remained static once it appeared in the environment. Here, the optimal path was planned. The obstacle will appear in the environment blocking the mobile robot trajectory, but the obstacle will not remain static. It will be moving with a predefined trajectory. This problem is more complex because it faces the path planning algorithms to make their optimization work over a noisy surface. Hence, at every iteration, the searching zone might be different. The experiment was conducted as follows. The start position of the mobile robot and the goal position is defined. There are 3 obstacles in a coordinate position to recreate a real world wall. A dynamic obstacle in the position is unknown for the mobile robot. As a consequence of this condition, the dynamic obstacle is not considered for the initial path planning, which is shown in figure A. At this point, the path planning is considered offline. Next, once the optimal path was obtained in offline mode, the mobile robot starts to navigate in an online mode. When the mobile robot is at the position, it detects a new obstacle, which is not considered at the offline path planning stage, which is shown in figure B. Now, the new obstacle is moving and eventually it will obstruct the path of the mobile robot. At this point, the BPF proposal starts to recalculate a set of parameters to avoid colliding with the mobile robot. By updating the optimal path to reach the goal in an online mode. Figure C shows the updated path for avoiding the moving obstacle. It is worthwhile to note that eventually the results will tend to be very similar due to convergence of these algorithms. However, the strength of BPF is that the bacterial evolutionary algorithm in this application usually needs fewer generations to provide optimal values. Therefore, it is fastest method leading to the reduction in computational burden. Here are a few remarks. In GPF, this method was capable of obtaining the optimal path. In an online mode, the path to reach the goal is longer than the obtained path by PBPF and BPF, but it is comprehensively good. PBPF performs well working online and it requires less queue positions than GPF. BPF approach provides the best results. It finds the shortest path to reach the goal with less queue positions and consistently to previous experiments. This is a summary of the execution times to reach the optimal path value of every test problem and shown below in the table. In this table, we let run the algorithms until they find a feasible path and they fulfill the optimization criteria. Hence, the BPF last fewer generations than the PBPF and GPF, although there were only 2 to 4 generations less. It is significant since the fitness function, which was in the algorithm 3, requires to perform many operations, making its calculus computationally expensive. The average time for each implementation, that is sequential and parallel, of each algorithm was computed, with the aim of calculating the average speedup between PPF and PBPF as well as GPF. In all the cases, the speedup was significantly good, and you can just take a look into all the other time taken by the sequential and parallel processes for the various test problems shown on the left. So this is a conclusion slide, and let's talk about the first point, which is we proposed a novel method for path planning called Bacterial Potential Field, which ensures to find optimal paths in complex real-world scenarios with static and dynamic obstacles. Second, it uses a bacterial evolutionary algorithm to find the shortest path or optimal path. Third, considers the mobile robot's physical size and orientation in the plane. 4, demonstrated the bacterial potential field and it outperforms the GPF and PBPF methods by reducing the computational time to find the optimal path by at least a factor of 1.59. When it comes to future work can be expanded to very complex sceneries in 3D containing multiple static and dynamic obstacles of different sizes. Evaluation of the BPF method in parallel mode demonstrated that this can be a high performance, highly scalable method and can be implemented using CUDA. And since it is highly scalable, it can also be used with new technologies such as GPUs. Third, it can be extended and applied to driverless cars. And here in the figure, you can see a slide or a presentation given by Mr. Drago, who works at Waymo. So he talked about how Waymo uses attractor potentials and triple potentials for motion planning of its cars. You can see the path planned is the attractors, and it has the dotted points, which are the attractor points, and the repellers might be the cones on the roads or the pedestrians on the right of the roads. So this is a really nice application of potential fields in autonomous or driverless systems. And the final would be planning and coordinating the motion of multiple mobile robots for missions such as reconnaissance or mapping, where mapping using one robot is very time consuming when compared to multiple robots. And this concludes the presentation. So if you do have any queries or questions and doubts, please do feel free to comment on the video or send me an email. Thank you.